So, of course, those presentations are meant to be interactive, but since we are limited with 40 minutes per presentation, of course there will be a limit to how many questions we can answer, but we will have a discussion period at the end of the workshop. So, if you cannot ask all the questions you would like to ask, write them down. Okay? Oops. All right. Everything okay so far? So, as I told you, I'm going to talk about analyzing natural language requirements. And why we have a significant activity actually here with several industry partners around that topic. Why that? Why do we do this? The thing is that despite 30 or 40 years of research on formal methods, the fact of the matter is that when companies write down requirements, which is not always the case, but which is the case in many domains, such aerospace, automotive, finance, and others, they are mostly natural language form. Now they come in different forms, as we will see. It can be simply natural language statements, it can be user stories, it can be use cases, it can be a mix of natural language and models, but there is always a significant natural language component. And people use those requirements for many different reasons that I will discuss. Another thing to realize is that, of course, when you want to analyze natural language requirements, the natural technology to use is natural language processing. And natural language processing has made huge progress in the last 5 to 10 years. I mean, it has nothing to do to what it was 15 or 20 years ago. I mean, it doesn't even start to compare. I guess it's a bit like machine learning. Yeah. But machine learning was actually quite advanced 15 to 20 years ago, except that there was no data. And the computers were not that fast, or as fast as they are today. But it was quite advanced already. But natural language processing has completely changed. And is in part actually based now on machine learning. That's why it's becoming very effective. And now it's possible to actually apply NLP to develop practical and scalable solutions, as I will show you. However, of course, there is no practical and scalable solution without taking into account the specific context factors and without making working assumptions about the form of those requirements, how they are documented. So there is no universal solution. So what I will do is that I will report on a variety of research projects with industry where the objective and applications are different. My examples are from automotive and satellite, but actually it applies to every context where there are natural language requirements. And I will try to draw lessons learned at the end of the presentation. So I have applied NLP to requirements in many different contexts with my colleagues here. Simply, for example, verifying that requirements comply with a template, which is important in practice, and it's not easy actually to automate, as I will show you. Performing change impact analysis, you change a requirement, what other requirements are impacted, what design decisions are impacted. Domain knowledge extraction, I will explain what that is, just wait a few minutes. Assess requirements completeness to the extent possible. Requirements-driven testing, this is green because I will not cover it in this presentation, but Fabrizio will cover that topic in this presentation. Requirements-driven testing, which is an extremely important application in many domains, where you need to show traceability between system test cases and requirements. There are many domains where this is very important. And product line configuration. In this, because of time constraints, in this presentation, I will only cover the topics in blue. But I just wanted to tell you that there are many, of course, many more applications in which we have been involved here, and many more applications in general, and there are references at the end of the series for the topics I will not cover. So checking compliance with templates. So what I'm going to present actually is a result of a project that took place with a satellite operator we have been working with for 5 years, which is SCS. And of course, in that context, they are very large projects. They develop ground control systems for satellites, systems that are quite not only large, but that involve usually many stakeholders. I mean, it's quite common to have 12 companies working on developing such a system. And of course, they have hundreds of natural language requirements. In their case, they are statements. Okay? They are not use cases or user stories, they are statements. And those requirements, basically, are used as a contract among all the stakeholders. So they are very important. They are not only important to make sure there is no misunderstanding in terms of what the objectives are, but they are very important in the sense that they are actually a legal contract. But the problem is that they also frequently change. That's another problem. So it's a contract that is changing. Of course, they want to minimize ambiguity and incompleteness in the requirements. And one way that people have been doing that for 20 years, at least, is to use templates. There are a number of templates that exist. I will only show you the simplest one, but there are quite sophisticated templates. One thing that they have noticed, of course, this was 5 years ago when we started this, is that when there is no automated way of doing quality assurance of requirements, people tend not to comply with the templates. If they are not forced to, they don't comply. So there was a need, also because of the large number of requirements, there was a need to automate the verification to templates. That was the only way to achieve that. And it needed to be, of course, scalable and accurate. I mean, if you have a lot of false positives, if you keep telling people, it's a bit like compiler warnings, if you keep telling people that they have done something wrong and those are false positives, nobody's going to pay attention. So, and there are tools that exist, there are commercial tools that exist, but they are not practical in the sense that they require a glossary or an ontology of the domain. They require you to define all the concepts and all the phrases that are specific to the domain. And of course, nobody does this. Or nobody does this in any complete way. That's another thing you have to take into account. And SCS definitely did not this. So here is the simplest template that exists in terms of requirements template, but it's called RAPS, but there are many more sophisticated ones, such as EARS, is the one that is used at Rolls-Royce in the UK and worldwide, for example, and now used more and more in different places. EARS as in E-A-R-S. Okay? But this one is the simplest one, and it doesn't really matter what the template is. We have actually worked on different templates in our tools. Usually the requirement is divided into a number of segments, and here is an example, a sanitized example from SCS, where you have a condition for a statement. As soon as the visual notification is presented, you have the system name, you have a mode, a verb mode, which says how important is the requirement, shall, should, will, the usual thing. You have actually the functionality itself, which can be expressed in different ways with certain keywords, provide someone with the ability to do something, or just do something, or be able to do something. And you have the object to which the functionality applies, for example, the local SNT application. And you have additional details about the object that may describe the object in different forms. So here, this is meant to help people make sure that nothing is missing in their requirements, and that somehow they are, not as they are, as clear and as precise as possible. But of course, the problem is that it's not easy to make sure you comply with such a template. Why? Because you have complicated domain-specific phrases such as this one here. And if you don't have a glossary, then it becomes very difficult to make sure you properly delineate all the segments in the statement sentences. And that's why most of the commercial tools require a glossary. But of course, the problem is that in practice it doesn't exist. So then we had a dilemma. So what we did, and again I'm not going to go into a lot of details, because my goal is to give you an overview of a number of applications, and I will more or less finish template compliance checking with that slide. Is that we use a technique called text chunking that I will illustrate next, which automatically identifies segments in a sentence, basically noun phrases and verb phrases, mostly, which is what we're interested in, without performing expensive analysis or without performing expensive parsing, which makes it scalable. And we have, of course, algorithms that tell us when we need to perform expensive parsing, which is in only rare cases. So most of the time we use text chunking, which makes us scalable. And we have performed compliance checking on both rep and ears. We don't rely on a glossary and an ontology. And we can analyze hundreds of requirements in a few minutes, which makes it practical from a quality assurance standpoint. And text chunking is basically, it's a technique that takes a statement like this and identify noun phrases, verb phrases, subordinate clauses, prepositional phrases, adverbial phrases, etc. Of course, it's not that simple. We had to come up with a number of tricks to apply. I'm not going to go into details. You have references. We evaluated it, of course, on actual industrial requirements in the nuclear domain, safety critical domain, the train domain, and the satellite domain, of course, with our partner, SES. And there was no, the fact that we didn't have a glossary had no impact on the accuracy, which is what we wanted to achieve. We had an average recall of 94%, average precision of 91%. We developed a tool, and you can find out about that tool on that website. And by the way, I forgot to say that Nadia is going to bring memory keys with all the presentations. Okay, so you'll have all the slides. All right, the second application is change impact analysis. As you know, it's not just SES, it's nearly every company that write on requirements. Requirements keep changing. And they have side effect on other requirements, on design decision, on test cases. I will not address the problem with test cases. Actually, traceability to recommended test cases will be addressed by the presentation of Fabrizio Pastore later on. But I will address the first 2 points. Change impact analysis of requirement changes on requirements and design decision. And how can we support this in a scalable and practical way? You know, if you make a change to a requirement and you have 1,000 requirements, you're not going to keep reading the 1,000 requirements to find out what changes. You know. So then what happens is that when you don't have effective automation, requirements become inconsistent and obsolete. And then you don't want that, especially when they are used as a contract or they are used for legal reasons. You know. And again, there was no technology we could use that was ready to use it. It doesn't exist. So the first thing I will present are inter-requirements change impact analysis. This was again with SES. And we basically, one thing which was clear, again, to make it practical, is that there is no way you're going to ask engineers for traces between requirements or dependency traces between requirements. That's not going to happen. So the only thing we have in input is a list of requirements, and that's it. Okay? And we propose an approach which is based on natural language processing again. This is, of course, the recurring theme of this presentation. And phrase syntactics and semantic similarity measures. As you will see, those are technologies that take phrases, words or phrases, depending on what is the unit of analysis, and perform both syntactic similarity measurement and semantic, based on the semantic of the language. And now there are very sophisticated libraries that exist that are very accurate and very powerful to do this, which was not the case, especially for semantic analysis, like 15 or 20 years ago, even maybe 10 years ago. So as you will see, we are able to accurately pinpoint which requirement should be inspected for when there is a change, a requirement change. So here is an example. Again, this is a sanitized example from SES, but we have done it in 3 different organizations. You have 3 requirements. You make a change. Okay, you replace this by that. Of course, that change can be syntactically identified. This is not very difficult. But what is the first thing you need to do is to understand what is the change precisely. Obviously, the change may not be just to replace help desk with document repository. But usually the change is to replace a phrase with another phrase. So you have to identify the right unit of change. Okay? Then the second problem, and this is something we noticed, and that we're still working on actually, is that you cannot do precise impact analysis if you don't capture the change rationale in some way. You have to somehow say why you're doing the change. And what does that mean? Let me show you an example, though I won't go into details. For example, here, the first example is that we may want to replace user help desk with user document repository everywhere in all the requirements. That's one possible rationale. In that case, all the 2 other requirements are impacted. However, it's not the only possible rationale. You may want simply to avoid a communication between mission operation controller and user help desk. And here, in that case, it's only requirement R3 which is impacted. Or you don't want any longer to transmit status reports to the user help desk, but instead to the user document repository. And then there is no impact. Only R1 changes. So I won't go into details, but basically we found an easy way for people to express rationale in order to guide the impact analysis. Okay? So to summarize, our strategy is based on accounting for the phrasal structure of the requirements, not just the syntactic changes. So we identify what are the phrases that are impacted. We also consider semantically related phrases that are not exact matches, and of course close syntactic variations as well. And we account for the change rationale. And we developed a tool again that is available here. And here you see all the different steps where we process requirement statements, we identify phrases, we compute similarities. We of course identify differences after changes are made. We capture the change rationale and transform it into a propagation condition. And then in the end we sort all the requirements according to the likelihood of change. And we did some evaluation in 2 different industrial contexts, where there were a number of known change scenarios in requirements, actual change scenarios. And we basically evaluated the approach by computing what we call the futile inspection effort, which is what is the percentage of requirements you need to analyze to find all the changes. Okay? And of course, you don't want to inspect a large percentage of the requirements because otherwise that would defeat the purpose. So as you can see, except for that outlier that we'll discuss in a minute, we managed to find all the impact, all the elements in the impact set by analyzing less than 10% of the requirements, and actually on average much less of 10%. But there was actually an outlier here, sorry, which was due to the fact that on the second case study, we didn't have a collaboration with the company. We just got the requirements and the changes. And we defined the propagation, the change rationale for the changes, as opposed to the requirements we had and the changes we had with the CS, with whom we were actually collaborating. You know. And of course, for one of the changes, we didn't define the propagation condition well, so, which led to that problem. You know. And also, out of 106 impacted requirements across the changes, we missed 1 impacted requirement. So we basically, in terms of recall, we achieved a very high recall. Yes?
What are the parameters that are affecting this percentage?
I think the main parameter is whether or not you have people who can define the change rationale. And that should be, of course, the people who are responsible for the change, which we didn't have for the second case study.
It's not all about the method, but the context matters.
I don't think so. Of course, if many of the changes affect a large number of requirements, then that technique becomes less useful. But in practice, as you may have noticed, that's not the case. Okay? But of course, it's possible that some requirements affect many other requirements from time to time. And if this happens very often in an environment, that may have an impact. And by the way, the reason why we missed that impacting requirement was the lack of domain model knowledge. You know, sometimes you need a domain model that tells you, for example, this is an example, that a touristic attraction is also a point of interest. You need to have an ontology of the concepts in the domain. If we had had that ontology, we wouldn't have missed that requirement. Actually, that was so actually, this is, you can also consider that as a factor that affects the results. So requirements to design. So here is a different context. This is with Delphi automotive systems in the automotive domain. And here in the automotive domain, like many safety critical domain, people need rigorous change management. They cannot make a change and not prove that that change is not affecting safety. And they have to be a bit careful about that. And so they have requirements, but they also have a design representation of the system at a certain level of detail in SysML, which is, as you know, a system engineering modeling standard. Okay? And this is commonly used, it's not just Delphi automotive system, it's commonly used in the embedded and cyber-physical systems world in general. So what we want to know is that when there is a requirement change, what are the impact on design decisions? And here, especially in a safety critical context, having a complete and precise design impact set is very important. You cannot afford to miss too many impacted design elements. So typically in SysML, you have a taxonomy of requirements that look like this, a requirements diagram with some text and some requirements ID, and you decompose upper level requirement into lower level requirements, like here. Then usually you represent the structure of the system as a block diagram, and here is an example. A block diagram with output and input ports. And usually what you do in SysML, you have a very coarse traceability between requirements and the blocks that directly implement those requirements. Okay? But it's very, very coarse. What you do also for most of the blocks is that you define their behavior, for example, using activity diagrams, or a specialized form of activity diagrams using profiles, profiles in the modeling world. So here's an example for block B3, Diagnostic Manager. And it links basically input ports to output ports through a number of operations. So, of course, the natural thing to do when you want to do impact analysis is to do structural and behavioral analysis of those diagrams. It's a natural thing to do. For the structural part, it's pretty straightforward. Let's say you make a change to requirement R11 here, over temperature detection. By just following the dependency links, you can identify all the blocks that are directly and indirectly impacted. The problem is that many of those are false positives. It's not really an option in a large system. So what we do is that we also analyze the behavioral diagrams, and we find out where on which input port the change propagates. And of course, we can then identify on which output ports the change is going to keep propagating. And we can find out, for example, that that port is not affected. So that helps. That helps eliminate some of the false positives in the impacted set. But it's not enough. In practice, not enough. It's still not precise enough. So here comes again the recurring theme of this presentation. Natural language processing comes to help us. So, what do we want to do with natural language processing? We want to come up with a rank of the blocks that are impacted according to the likelihood of impact. And even we want to know when, we want to have a threshold that tells the analyst when to stop looking for impacts. When to stop. Okay? And so the way we did it is that we took advantage of something. In the change management system that we call all the change requests, usually system engineers write an informal description of the change. So like this. This is an actual one. Temperature lookup tables and voltage converters need to be adjusted. They write stuff like that. And so what we do is that we compute similarity scores, both syntactic and semantic, between textual model elements and those informal descriptions that engineers write. Okay? And then we solve the disagreement obtained after structural and behavioral analysis based on the similarity scores. So, of course, so what we do, here's a diagram, we have a similarity score, we rank the requirements on the x-axis according to that similarity score. So you can see the similarity score is decreasing in a steady manner. But of course now we have to know when to stop. And what we do is that we compute the delta score between requirements, and we stop after the last significant peak, delta peak. Why? Because after, requirements cannot be distinguished, so there is no point. And there is a last peak usually, which is a mathematical artifact for a reason that I won't explain. There are a lot of details. You can find that in the paper. So we found a way to tell them when to stop. And of course, we developed a tool that implements all those steps. That was used with Delphi. And we performed an evaluation with 16 change scenarios. And here, the goal is to show you that why NLP is useful. If you do structural analysis only, this is a futile inspection effort. It's all the elements that you inspect for no reason, basically. And it's quite high. If you do behavioral analysis, you go down significantly, with an average around 10%. And if you use NLP, you are down to 5. So you have the number of other elements that you have to inspect. Okay? We also here missed one impacted element out of 81. The last application of NLP, natural language processing for requirements, is extracting domain knowledge. This is maybe a little bit more subtle if you haven't had that experience before. So I need to motivate this. When you read requirements, all requirements are based on domain concepts. If you don't know those domain concepts, you read the requirements, you have no clue what the requirements are saying. You have seen examples before from the satellite domain. Okay? Concept related to ground control system of satellites and antennas and converters. If you don't know what all those concepts are, you have absolutely no clue what the requirements are saying. So, very often, that terminology, those concepts, unfortunately, are not consistent across stakeholders. People, when you have large projects involving different companies, people of different background, there is a lot of confusion in the concepts and terminology that is being used. So people usually have developed glossaries or even domain models, which is a more sophisticated version of the glossary, or complementary to glossary. And I'll show an example. So a glossary, of course, is simple. It's a set of concepts and their definitions. A domain model is a bit more complicated, and I'll show an example in a minute. But anyway, it's something that aims at creating a common understanding. And software engineers cannot solve that problem by themselves because very often also they don't have a very deep knowledge of the domain in many contexts. or not all of them, at least. So let me start with glossary extraction and clustering. I'll explain what that means. So of course the goal is to mitigate ambiguities and to help make sure people achieve consistent terminology and improve communication. But one thing which is very important is that you might think that from a rational standpoint, people should define a glossary before they write requirements. But in practice, of course, they don't do that. Nobody does this. Often you start with no glossary or you start with a very incomplete glossary. So what that means is that you somehow need to extract or help people extract glossaries from requirements as opposed to using glossaries to write requirements. That doesn't sound very intuitive, but that's practice. So we developed an approach which is basically 3 steps. One, of course, is to identify the candidate terms based on a combination, based on heuristics of combination and filtering that I will show in a minute. We also measure similarity between the terms or the phrases that are being extracted in order to group them and cluster them. And I will tell you why clustering is necessary in a minute with an example. And then, of course, you have the clustering itself based on the similarity calculation. And usually we use a clustering algorithm that doesn't require to know the number of clusters in advance. So if I take an example to illustrate, a trivial example to illustrate those 3 steps, let's say you have 2 requirements, again, sanitized from our satellite example. We first identify phrases that are worth including into the glossary, and there are many technical challenges, because as you will see, we don't only extract noun phrases, we also extract combination of noun phrases. You know, you have the possessive S here, you have a noun phrase here and a word here, which is also a noun phrase. So we also have to extract and recognize combination of noun phrases that should be in the glossary. Then we compute similarity between those different terms. And then we cluster them. And why do we cluster them? Because it's a way to identify inconsistencies. You are going to find in some clusters things that are semantically related, but maybe that may correspond to identical concepts expressed in a different way. Okay? So it's a way to help with consistency. So we did an evaluation in 2 different environments. We compare our approach with a number of tools that exist actually to do that, except that they don't do any clustering. They just do the term extraction. We had a much higher recall and a similar precision. But of course they don't do clustering, so we couldn't compare the clustering accuracy. We also did an interview survey with domain experts, and we asked them whether they found the clusters helpful in identifying the related terms of a glossary, whether it helped them to define glossary terms more precisely, and whether they could identify variations of the same terms and somehow resolve inconsistency problems. And the feedback we got was largely positive. For the last one, you have 28% not relevant because you don't always have variation in a cluster of the same concept. It doesn't always happen. And the last thing I will cover very quickly is the domain model extraction, which is very similar to the glossary extraction, except that when we extract as a domain model, we can imagine that as a class diagram. It's not just a list of concepts and terms, it's concepts and their relationships and their attributes. So it goes a bit further. Okay? And very often people in many domains, in many application domains, like to rely on such domain models because it's complementary to the glossary. The glossary provides a textual explanation of the concepts, and this provides you with relationships between the concepts, if you will. And here is an excerpt, a sanitized excerpt from the satellite domain again. So of course the problem is that building those domains manually is a nightmare, and especially when you have a lot of stakeholders, inconsistencies. So it is automation. There are approaches in the literature, but they usually assume that the natural language that is used is very restricted. It's not free. They only manage to extract direct relations between concepts, not all relations. And there are almost no empirical results on actual industrial requirements. So anyway, we develop an approach where the first step is more or less like the previous one. We process the requirement statements. We identify the phrasal structure of the requirements and the direct dependencies. And then we do two other things that I'm going to explain now. One important one is what we call leaf dependencies to semantic units. So imagine you have a requirement like this. So you have direct dependencies. This is a normal subject dependency, a direct object dependency between initialize and operator, in between initialize and configuration. So you could derive that direct relationship between operator configuration. But the thing is that it's not necessarily the most interesting or the only thing to derive for a domain model. We want to analyze, also identify more indirect relationship, and we want also to leave those dependencies to identify, for example, dependencies between phrases, like system operator and simulator configuration. So that we get something like this as opposed to something like this. And for indirect relationship, when we construct the domain model, we use something called link path that comes from information retrieval. And what we want is not only to obtain something like this on a requirement like that, where simulators send a message, but we also want to identify such relationship. The simulators send a message to database. Simulators send a message to database via monitoring interface. So this is what we call indirect relationship. And we do that using the link path method. So we also assessed it. We got pretty good results, but I won't go through the details. Now let me just conclude with the discussion. I haven't had a chance to show you all the application of natural language processing for requirements. You will see more of that with Fabrizio. But there are many applications of requirements engineering. If you bother to define requirements in a rigorous manner, it has to be useful for something. And to be useful for something, you need some form of automation. Not only automation, that limits pretty severely what you can do with your requirements, and that decreases to a large extent the value of doing rigorous requirements engineering. There are many applications, some we have seen, others we haven't. Of course, it's used to have a shared understanding among stakeholders. It can be used to define a contract. It can be used to support quality assurance, which is doing requirements-driven system testing, support change control, as we've seen, and even support product line configuration. There are different forms of requirements, as I've said. So whatever you do with NLP will have to be adapted to the type of requirements you're dealing with. They come in many different forms. There is no best form of requirement. It all depends on the context, what people need to do with requirement, what type of system they are developing. There isn't a better way among the alternatives of defining the requirements. It's a trade-off, like everything else in software engineering. But no matter what, there will always be natural language, a significant natural language component. Those are the context factors that determine what type of requirements people usually use, the domain complexity and criticality, whether they have to demonstrate regulatory compliance to some authority, the project size, team distribution among stakeholders. Of course, if you have two guys in a room, developing a web system, your needs in terms of requirements engineering here are much lower than in other contexts. The background of stakeholders and communication challenges, etc. There are a lot of aspects that directly impact how you do requirements engineering. No matter what, automation is required, otherwise it's going to be difficult to justify the cost of rigorous requirements engineering. And in most cases, and I've shown you examples, but I could have shown you many more examples, we don't have practical and scalable solutions on the commercial market. So, to conclude, NLP technology has made a huge leap forward. It provides many opportunities for automation. But there is a need for more research on analyzing natural language requirements using NLP. There isn't that much research. There are very, very few papers that are being produced every year. There are many applications, a diversity of context and types of requirements, which means that the research scope is very large. You don't have much research, and the scope of research is very large because requirements come in different forms, applications are many. So that's, there is a lot to do. And we need to account for practicability and scalability. And we need, more particularly, more reported industrial experiences. Because, of course, the working assumptions you make in terms of how the requirements are formed are very important. And you cannot make working assumptions if you don't work in a real context. So you cannot find out about that. So that's all for me. You will find references at the end of the slides. And I guess we have 1 or 2 minutes for questions, if there are any, or comments. Yep.
I think this is based on natural language.
Yes.
Is it the results, would they be dependent on the actual language you're using? That's one question. Second question, if I would change language, if I do perhaps modeling at a low level in English, but write the first requirements in Chinese, let's say,
yes.
What would happen then?
Yes, it's a very good point. It's pretty clear that NLP technology in English is more advanced than in most other languages. That's clear. However, there is more and more technology available, even for example from Google. Now Google has NLP technology. And they are also making quick progress on other languages. For Chinese, I don't know. I don't have that. But for example, we had to use NLP for French, because we have a few projects where we analyze legal text in French. And it's getting pretty good. But of course, you're right, for some of the languages, the technology might be very limited. And I don't know for Chinese. I don't know if anybody knows about that here in the room, but I don't.
Just check to be sure. Google acquired API.ai, which is an engine to understand basically intent from natural language. And before they didn't have Chinese, but now they have 3 flavors of Chinese also.
Thank you.
Don't worry, there are many technology can have some NLP technology can help process any language.
Any other comments?
For the feedback, sounds very predictive. That's from industry. I remember this. There's a feedback, right?
Yes.
Say the 60% predictive, something like that.
Yes.
Is that from industry? Which industry?
Here, the examples I've shown here are from automotive and satellite. But of course, we have worked also in the legal domain. We have worked in other. We are also working in the financial domain. But those are examples from automotive and satellite. But I don't think that a lot of the stuff I presented is in any way specific to automotive or satellite. Except for CSML, sorry. The use of CSML for design representation. This is, of course, more. It tends to be used for cyber-physical systems and embedded systems. That's all.
Back to CSML, just out of curiosity, with your behavior analysis, did you also face any false negatives? Because your tone sort of implied that you're only taking care of false positives in the...
No, I've shown that we missed one element out of 81.
For CSML, yes.
Yeah, we missed one element of 81, actually. So there are false negatives, but they are very few based on what we've seen so far.